Okay, how's it, Chase? We've got a couple of sections left to do in chapter 5, so hopefully I can get through them today. I really hope so that we can finally get onto differentiation and integration. And yeah, so let's get cracking. Okay, so we are now on section 5.22. Okay, 5.22. This is the graph of y equals a sine bx and y equals a cos bx. So they basically ask you draw the graphs of y equals 3 sine 2x and y equals 2 cos 3x on the same axis system. Okay? And then what they do is, okay, so they take y equals 3 sine 2x and y equals 2 cos 3x, and they just get the information from here. That means amplitude is 3, and this means that frequency equals 2. Here, amplitude equals 2 and frequency from here equals 3. So so they basically, what's a bit irritating to me is that they didn't bother to explain any of what they've actually done here in this example. By the way, this is example 40. Forgot to mention that. Example 40. They didn't bother to explain any of what they're doing here. Basically, what they've done is calculated the period of your graph. And yeah, so what they've done is basically, if you've got a graph, a sine graph, so the graph, this is the graph of y equals sine x, which means that it ends at 360 here. Well, it continues, but one graph in one repetition or one period. A period is the amount of degrees it takes the graph to do a full repetition. So here the period is 360 degrees, amplitude of 1. Okay? And the same goes for cos x. The period of your cos x graph, your standard cos x, which is y equals cos x, this is also 360. So you see it does half of an up, then a full down, then half up. So it has a period of 360, because that's one repetition in 360 degrees. So period, which is represented by t, equals 1 over frequency, okay, times 360 degrees. So if you've got a graph with a frequency of 2, then period equals 1 over 2 times 360 degrees equals 180. Okay, so we know that this graph here has a period of 180 degrees. This graph has a frequency of 3, so t equals 1 over f times 360 equals 1 over 2 times 1 over 3 times 360 equals 120 degrees. Okay, and we also know that the amplitude of this graph is 3 and the amplitude of this graph is 2. So how do we draw them? Okay, I'm going to draw this first graph, which is our sine. I'm going to draw that in red. So if the period is 180 degrees, that means, let me just draw some points here. 90, 180, 270, 360. Okay. If the period is 180 degrees, that means that the graph goes up and down in 180 degrees. And it always crosses the axis in the middle. We also know that this is a sine graph, so it means it's going to start at the origin. And we know it has an amplitude of 3. So it starts at the origin, climbs up to 3, goes down to -3, and ends. Okay, so it needs to do a full up-down in 180 degrees. So it's going to look like this. See, it crosses the x-axis in the middle, which is 90 degrees. Okay, and there you go. There's your terribly drawn sine graph. And this point is 3, because our amplitude is 3, and this point is -3. Okay, now let's draw our cos graph. This one has a period of 120 degrees, an amplitude of 2, and a period of 120. And because it's a cos graph, it starts at its peak, which in this case is 2, and then it drops down. This would be at 90, and so on. Okay, so I'll do that one in green for us. I just need to draw in a few more points here. Let's draw 45, 135, this is 225, this is 315. Okay, so it's a cos graph. We're drawing this one. It has an amplitude of 2, and because it's a cos graph, it starts at its amplitude. So it starts here at 2, and it's going to go, the period is 120, so within 120 degrees it will have done a full up and down. So it's going to go down there, up, down, and up, down, and up, and it'll actually finish over there. Okay, so this is a terribly drawn one, but you get the point. It goes once, twice, 3 times, because it has a frequency of 3. So it goes up and down 3 times in 360 degrees. And look, you actually needed to draw more points to draw this accurately, and this should only go down to -2, because the amplitude is 2. Okay, so there we go. We've drawn our graphs. Okay, so next in example 41, they talk about phase shifts. Okay, so in example 41, example 41, okay, they say draw the graph of y equals 2 sine 2x plus 20. Okay, so now they finally introduced you to the full form of your trig graph, which is y equals a sine bx plus c, and y equals a cos bx plus c. Okay, we already know what a does. A is the amplitude. We already know what b is. B is the frequency, and that doesn't change. So b and a are still the same. C is called the phase shift. And I'm just going to illustrate phase shift to you by an example. So let's do y equals 2 sine 2x plus 20 degrees. Okay. How does 2 sine x look? 2 sine 2x. Well, we've got a frequency of 2, which means it's going to do down and up in the space of it's going to go down and up twice in 360 degrees. So there's 360. We've got 180, 90, 270. So, and we know it's got an amplitude of 2, and it's going to go down and up twice in 360 degrees. So, it's going to look like this. Once and twice. That value is 2. That is minus 2. Okay, so what do we do with this plus 20? Okay, well, what a phase shift is going to do is it's actually going to, if this is positive, okay, so if it's positive, greater than 0, it shifts graph to the right, and if it's less than 0, I lie. It shifts graph to the left, and if it's less than 0, it shifts graph right. Okay, and that's basically all you need to know. So what's going to happen is it's going to shift our graph left by 20 degrees because it's positive. So basically what's going to happen? We shift all of our points left by 20 degrees. So instead of this point being at 90 degrees, so let me draw the points that I'm using. These points, that was 0, 90 degrees, 180, 270, 360. So all that's going to happen is these points become shifted to the left by 20 degrees. So we shift this point to the left by 20 degrees. We're here at minus 20. That is going to be how much? 70. That is going to be 160, 250, 340. And we end up with the exact same graph, just shifted by 20 degrees. And that's really all there is to it. So the amplitude doesn't change with the phase shift, it's just that the actual position of the graph shifts. Okay, so we shifted to the left by 20 degrees. And if that was a minus 20, so let's say if that were a minus, then our graph would have shifted to the right. So it would have looked something like this. And there you have it. That's all there is to it. And the same applies to cos, a graph of cos. Shifts the graph left if the phase shift is positive, and it shifts the graph right if the phase shift is negative. And that's really all there is to it. The same goes for tan. Exactly the same story for tan. It shifts your entire graph left or right, and it'll also shift your asymptotes in the case of tan. But yeah, I'm going to stop there as far as the trig graphs go. I'm sure you can figure it out from here. One thing to note, on page 5-57, example 8, you'll see they ask you to draw the graph y equals 4 cos 2x plus pi over 6. Just note here that this is now radians. So either you do your whole graph in radians, or you can convert it to degrees and draw it in degrees. Completely up to you. Pi over 6 radians, you would convert that to degrees by saying degrees equals radians over 2 pi times 360. Pi over 6 is, I believe, 30 degrees. Okay, so that's the end of trig graphs. And yeah, if you've got any more questions on it, I'm happy to help. So then we're going to move on to the cubic graph. And once we're done with the cubic graph, we will be done with chapter 5. Now that's fantastic. Okay, cool.